Welcome back to the today's class. Today we are going to discuss about digital adders. Digital computers perform various arithmetic operations. The most basic operation is the addition of two binary digits. So all the applications which you are using being of digital in nature. So these applications have some mathematical calculations. So these mathematical calculations include addition, subtraction, multiplication, division and so on. So the basic operation of addition is done with the help of adder circuits. The simple addition consists of four possible elementary operations. So the four possible elementary operations are: you can add the two inputs. These two are the inputs and the output is this one. So the two inputs may change with respect to the nature. So it may be 0 0. When added it will gives out 0. When 0 plus 1 added gives out 1, and 1 plus 0 added it gives out 1. If 1 plus 1 is added, it gives out 1 0, which represent it is having a carry out. The first three operation produces sum whose length is 1 bit. The last operation performs sum, output is 2 bits. So in this case the three operations which we are carried here has an input length, that is the output length of 1 bit, whereas the last operation you carried here has an output of 2 bits. The highest significant results is called the carry and the lowest significant bit is called the sum. So this represents the sum and the 1 represents the carry. The logic gates which perform the operation of addition of two input is known as a half adder, and similarly the logic gates which perform the addition of three inputs is known as a full adder. Half adder. Half adder needs two binary inputs and gives out two binary outputs as sum and carry. So this is the block diagram of a half adder. Here you need to give two inputs A and B as input to the half adder, and the output from the half adder is carry and the sum. The representation of half adder is shown here. The truth table of the half adder is shown here. Okay, if you see the truth table, this A and B are the inputs and the outputs are carry and sum. So you know that the addition of two input A and B, 0 plus 0 will represent the sum of 0 and there will be no carry. And similarly 0 and 1 is added, you have a sum of 1 and the carry will be 0. And similarly if 1 and 0 is added, carry will be 0 and the sum will be 1. If the two inputs 1 plus 1 is added, the carry will be made to be 1 and the sum is 0. So this is the basic of half adder and this is the truth table of the half adder. The K-map representation of half adder can be obtained. So you know that there are two inputs A and B and you are having two outputs, so you can map the input with respect to the output. So what you need to know here is regarding the K map, you need to draw a line like this. Okay, after that you need to put 0 1 0 0 and and you're going to make 1 1 over here. Then you are going to write the two inputs, that is A and B over here. After doing this thing, you can see the mapping of the sum. Okay, when 0 and 0, the sum is 0. So if there are two things, this is 0 and this is also 0, you put the 0 here. Okay, then for 0 1, you have to put sum is equal to 1. 0 0 here and 1 is here, you put that the sum is here. Okay, And similarly for 1 and 0, that is 1 is here and 0 is here, so put the 1 over here. Similarly for the next step, you can see there are two ones. Okay, two ones represent 0, so you make this here. So what happens here is this is the K-map constructed for the sum. Okay, this is the K-map constructed for the sum. For this K-map, you can see this bit and this bit represents the values, which represent, you can say this one will be a bar, because you are having 0 over here, you should write it as a bar, and here you should write it as a. Similarly here also it is b bar, and in the above category it is b. So if this is 1, you should write a and b bar. Okay, you should write a and b bar, because here this element is 1, this element represents a and b bar, so you should write a b bar plus, and this element you should write a bar b. Okay, this is for the sum. Similarly for carry, you can see here it is shown that the K-map is drawn, and you can represent you are having only one element in carry when both these things are 1. So you should have only one over here, and this element here it will be a, and here it will be b, so the carry will be a into b. So this is represented as carry. The logic representation of the half adder can be easily determined. So how it is determined here is, you can see the carry first. So if you see this is the carry, you need to multiply a and b. To find the carry, you need to multiply a and b. So 1 into 1 gives you the carry, whereas the other things, 1 into 0 is 0, 0 into 1 is 0, and 0 into 0 is also 0. So you have find you should AND gate. You have to AND the two inputs. So you have to draw a AND gate like this. Okay, these are the two inputs A and B. So you have to draw a AND gate like this. Okay, after drawing this, you will get the output of AB, which gives the value of carry. Okay, next, the next step. In the next step, you can see the summation. For the summation, you need to have a XOR gate. So XOR gate, that is the formula to find the sum of the two elements is a b bar plus a bar b. To find this, you can use the XOR gate. To connect the XOR gate, you can connect it with the above thing like this. Okay, you take the wire from here. Okay, then you connect it like this. Okay, after that you connect this thing like this, and then you will get the output A XOR B. Okay, this is the process of half adder. Next, for full adder, the full adder is also a combinational circuit which performs the arithmetic sum of 3 inputs and gives out the output bits. Okay, for full adder, you know that you are going to provide 3 inputs. The 3 inputs are A, B and C in. C in is the carry of the previous made addition. So you get A, B and C in, and you will get the full adder, and the full adder will provide you the sum as well as the carry output. The two input bits represents A and B, which is to be added, and the third bit is the carry bit C in. Okay, so you are going to add A and B. After adding this A and B, it will provide you a result, and this result is going added with the carry bit. After added with the carry bit, you have to give it with the carry as well as the sum bit. The next stage, you can see the two inputs are same, and then the carry bit is made to 1. Once it is done, since the carry bit is 1, you are getting sum of 1. And similarly in the next you can see 0 1 0. In this stage while adding these things the sum will be 1. And similarly if you add this a, b and c in 0 1 1, here there are two ones, what happens, the carry bit will be 1 and the sum is 0. And similarly for the next stage you are having a as 1, b 0 and c is 0. This causes carry to be 0 and sum to be 1. And similarly in the next one you can see the a is 1, b is 0 and c is carry is 1. So what happens, there are two ones, so that the carry will be made to 1 and the sum will be 0. And similarly the next stage, the a and b is 1, carry is 0. It represents carry is 1 because a and b is 1 and sum is 0. And the last step you can see both the carry and the two inputs a and b all are ones. This causes the carry bit is also 1 and the sum bit is also 1. So for this you can represent these things in the K map. So I will help you. Okay, this is 0 0, this is 0 1, this is 1 1 and 1 0. Similarly here you are having 0 and you are having 1. Okay, you can write a over here and then you can write bc over here. Okay, after doing this you need to know this is the input a, b, c is 0. First you will do for sum. Okay, first we can do this for sum. For sum you can see when all these things are 0 the carry and the sum is 0, so this one is 0. Okay, next you can see for 1 here c in is 1. Okay, for c in is 1, a and b is 0, so a is 0. Okay, a is 0 over here, b is 0 and c is 1 here. Okay, so what you should put here, it is 1. And similarly for the next stage here b is 1. Okay, so a is 0 and here you can see b is 1 and c is 0. Okay, this causes this one has a sum of 1. Okay, so this bit will become 1. For the next stage you can see b and c is 0, so b is and c is 0 over here. Okay, b and c is 1 over here and a is 0, so this causes this one. Okay, in the next stage you can see a is 1, b and c is 0, say a is 1 over here. Okay, and b and c are 0, so this causes the output 1 here. Similarly in the next stage 0, so this will present. And here in the next step you can see it is 1, a and b is 1. Okay, a and b, a and b, a is 1, b is 1 and c is 0. Okay, for that you will get 0. Okay, and similarly for the next thing also you will be when all these things are 1 you will get again 1 over here. Okay, this one is 0. What happens, you will be getting a equation like this. Okay, you have 1 over here, you have another 1 over here, you are having another 1 over here and you are having another 1 over here. In this case the equation of the sum. Okay, we will start from here. For this one you will get sum will be equivalent to a bar, b bar and c plus, for the next thing you can see b is 1, c is 0 and a is 0. So what happens here, you will get a bar, b, c bar. For the next thing, for the next one over here, for this one you are going to have a as 1, b and c bar as 0. Okay, for the next one, for this one, you will be having a as 1 and bc, okay, and bc. So while simplifying this equation, you can use an XOR gate. A XOR b plus XOR c will be the sum output from the full adder. Similarly, for the next stage, that is when you calculate the same thing for the carry. For the carry also we can calculate. For carry, if you do the same process, here you will get A, and here you will get B and C, and here it will be 0, and here also it will be 0, and 0 1 1 1 and 1 0, and similarly you will be having 1 here. So for this stage, you can see that for the first one, you can map only the ones, okay, then it will be easy for you. For this, you can see this one is 1, okay, carry here you are having 1. To do that, b and c is 1, okay, b and c is 1 over here, but a is 0, then you will get a 1 over here. And similarly for this one, a is 1 but b is 0, okay, a is 1 but b is 0 and c is 1, then you will get a map over here. Then for the next two things, you can see a is 1, b is 1 0 and another one is 1 1, okay, so you will get a map over here. So while you are finishing the k map, you will look like this. So then you have to group the components. So while grouping, you can group these two things like this, okay, and you can again group these two things like this. After that, you can group these two things like this. So while applying this grouping, you may come to know that the carry will be equivalent to AB plus BC plus AC. Okay, how this happens? While you group these two things, you will get AB. How you get AB here is, here you can see here A is 1, but in this above section you will be having B bar and C bar C, and in this thing you will be having B and C. So while taking these two things as common and A is here, you need to write the A over here. When these two things are common, you can see here B bar is there and here B is there, so cancel these two things. So what happens, you will get C. You can write AC directly over here, okay. Similarly, you have to simplify all these two things and you can get the carry signal. So this is the complete truth table representation. After having the representation and the equation in your hand, you can directly draw the logic gates. So how you need to draw is, you know that the XOR of A, B and C will give you the sum. So this is A, you have connected with the XOR, and this is B, you have connected with the XOR, and another one is the thing which is connected over the XOR. The output of this XOR is being connected to another XOR where you get the sum. Okay. For the next thing, you know that the operation of AB plus BC plus AC will give you the carry. So for that, the summation of AB is here. You can see the summation of AB is present here. Okay, and the summation of C, okay, you can see the summation of C with respect to the output from the hexar is present here. This is because the equation AB plus BC plus CA is being simplified. The AB is term is being there, and you can see these term is being simplified so that you are getting one output from C. Okay, you are getting one output from C. Okay, and the another output is from A plus B. Okay, you can see this C term is simplified to single one. This two terms is being taken as an output from the XOR gate. This is the output from the XOR gate. After this thing, you need to sum. Okay, this is one thing and this is one thing. You need to sum the two values. To do the sum, you can use the OR gate. So you are connecting it with the OR gate. Then you will get the carry of the full adder. Then the realization of the full adder with the using two half adders. So to do this, you need two half adders connected back to back, so that the sum from the half adder and the carry from the half adder is being used by the second half adder. After that, the two sums which are being two carries which are being provided by the half adder is connected together with the OR gate, so that it will provide you the carry signal, and these outputs will provide you the sum. So today we have seen about the addition adder of a digital circuit. We have seen the half adder and full adder, which is being used in all digital circuits to add the signal, that is the add the data, digital data, to provide a useful output. Thank you.